Now, continuing with Floating-Point Arithmetic. Since I entered grades for a bunch of assignments today, practically caught up grading almost. In Canvas, you should be able to see a comment from me on these assignments, indicating where you lost points. And why. So if you have any questions about those, I might overlook something, then you just let me know. Okay. So where we left off, having seen how floating point numbers are represented, how they're stored, today focus will be on what can go wrong when working with floating point number system. So there's various issues that come about, but due to the limitations on precision and limited range of magnitudes that you can have. So certainly loss of precision. So these limitations can lead to significant inaccuracies when you're carrying out ordinary arithmetic operations. Okay, so here's an example of what can go wrong because of these limitations. So in this example, we're dealing with a floating point system. Just for convenience, we'll stick with base 10, and we assume 10 digits of precision, and then the range of exponents will be between plus and minus 20. So here are two numbers, x and y, that can be represented using a floating point system. So, 4 times 10 to the 8th for x. So that's well within the range of allowed exponents. And then y is 2 times 10 to the minus 6. So I go ahead and carry out addition, x plus y. So we have 400 million plus 0.00002. So what we have here is the exact result, but then expressing it in the more scientific notation, that'd be 4.00002 times 10 to the 8th. But then we have to represent this in the floating point number system. Now the exponent is fine, but we only are allowed 10 digits of precision. And this number right here has more digits than that because of this wide disparity in magnitudes between x and y. So when I take FL, float, of x plus y, that means chopping this mantissa after 10 digits. In other words, this 2 at the very end gets lost. So in other words, x plus y in the floating point system is just equal to x, because y was too small relative to x to even have an impact. So this is what this situation where we can have loss of accuracy. When you are multiplying and dividing numbers, what you're doing is you're multiplying and dividing in mantissas. In that case too, there's bound to be some digits that just fall off the edge. Okay, this is what I was talking about. If two numbers are widely varying in magnitude. So what happens here is, if a difference in exponents, so in this case we have 8 versus minus 6, the exponents differ by 14, which is greater than the precision. So anytime that happens, you are going to have some digits lost. Okay, so that's one problem, loss of information. Another issue is the rules of arithmetic don't necessarily apply. We're accustomed to, for instance, addition being commutative and associative and so forth. Addition is no longer associative. So you can only say that x plus y, the quantity x plus y plus z, is only approximately equal to x plus the quantity y plus z. There's going to be some error because of the order in which the numbers are added. Commutativity holds. So x plus y is still equal to y plus x in floating point arithmetic, but associativity is out the window. Okay. Questions so far about these issues? Those are the small issues. Now we get to the big ones. Overflow and underflow. This is when we violate the range of magnitudes possible. So here's another sample floating point system. So base 10, 10 digits of precision, exponents between minus 10 and 10. This is limiting, but it's just an example. So here are two numbers that are allowed within this floating point system. So then, again, we have that x is rather large, y is rather small, just like before. So now I compute y over x. And when I do that, I end up with this number, 7.5 times 10 to the minus 15. Well, this exponent is below the lower limit. Exponents can only be, in this system, could be only between minus 10 and 10, and outside of that range, you get minus 15. So this is called underflow. That I brought up last time, when a number is too small to be represented in a floating point system. Now, underflow is not a big problem. You just declare it to be 0. And so that your computation can proceed. Now, if you were counting on a non-zero number because you were going to divide by it later, then you do have a problem. But overflow is relatively negligible as an issue compared to the opposite, overflow. So if I do x over y, so large number divided by a small number, I get a 1.33 times 10 to the 14. So 14 is outside of a range of exponents. It's greater than capital U. So that's an example of overflow. As we saw last time in the IEEE system, we have overflow. It declares the number to be infinity or minus infinity. Thing is, your computation after that point doesn't really make much sense. I mean, IEEE will perform operations with infinity, minus infinity, or NaN. It's just going to be total garbage. Okay. Now, I'm going to call to your attention one of the homework 3 problems. So the section 2.2 homework that's coming up next. One of the problems, and this one just really stumps everybody. And I give hints, and most are still stumped, and it drives me insane. So you warned up front, and you really want to put your thinking cap on extra hard for this one. The problem is about this. You have this expression, z is the square root of x squared plus y squared. And if we assume that x, y, and z, the exact values, can be represented in the floating point system, explain how something can still go wrong, even if x, y, and z are okay. Your input and outputs are legitimate. But some serious issue with floating point arithmetic can go wrong in computing this expression. Okay, so that's one thing. And people can have an idea. I think students generally figure that part of it out. The part that they really have trouble with is the other part of the problem. How can you rewrite this expression so that you're still computing the same value, but in a way that avoids the issue that comes up? Okay. So I look forward to y'all struggling with that one when it comes.
We look forward to to us struggling with that one when it comes?
Well, I'm being sarcastic. I'm not really looking forward to it because we're all going to be frustrated by it. You all for having a hard time with it, and me for my hands not making a dent. So it's just a ritual I go through every 2 years, and I'll bet actually this Friday's working on it right now. Okay. Don't put it in your pack. Go.
You challenged her.
What?
You challenged her.
Yes, I did. Okay. All right, now, here's an especially serious issue with floating-point arithmetic called cancellation. I have mentioned this before. What I told you about on the very first day of the semester, what happened in the 1991 Gulf War, where American troops were killed over this subtraction becoming inaccurate because the numbers being subtracted became very large while the difference between them remained small. So catastrophic cancellation occurs where numbers x and y you're subtracting, they are a result of prior computations, which means they already have some error in them. Or maybe they have errors in measurements of some kind. And then you form a subtraction where x and y themselves are much greater. So remember this notation, the double greater than sign means much greater than the difference between them. Okay, so why is that? Here's an example. So here, the sample floating-point system, 10 digits of precision, base 10. And so here we have these numbers x and y that are very close to one another. So we have 10 digits represented here. And in both numbers, the first 7 digits, the leading 7 digits of these two numbers agree with one another. So because we have 10 digits of precision, the relative error in x and y by inputs is 1/2 times 10 to the minus 9. That's what you get from the limits of your precision. But then I subtract them. I have these leading zeros because of all the cancellation, and then I have these 3 digits. So my floating point system has 10 digits of precision. My result has only 3 digits available. I've just given away 7 digits of precision. So this result is a lot less accurate than the numbers that were subtracted in the first place. So that's why cancellation is such a big problem. That's because most floating point operations you perform, generally speaking, the errors that you do introduce a little bit of error with every addition, subtraction, multiplication, division, but that error is usually pretty small. Here, the error can be extremely large. This is just one shot. Like you have your numbers that are nice and accurate, you do one thing and bam, it's all gone. It sneaks up on you. Now, what can be done in some cases is maybe you can rewrite your formulas in such a way as to get rid of subtractions that have this problem. Now, just keep in mind, subtractions themselves are not always bad. It's when you're subtracting very close numbers, that's what you want to avoid. Here's an example from linear algebra. And for those of you who are brave enough to take the second semester of the sequence, we'll see more of this. Okay. So let's suppose you're trying to solve a system of equations ax equals b. But we're not using the methods you learned in Math 326, where you're just doing your row operations and all that. Instead, you're generating a sequence of approximations, x1, x2, x3, that's designed to converge to the true solution, x. And you want to know when you can stop. So every time you compute a new x, like a new xk, you compute what's called a residual, b minus axk, because if xk is equal to the exact solution x, the residual will be 0. Because it's from here, b minus ax is 0. Now, if xk is converting to x, then rk is converting to 0. So the idea is to keep carrying out iterations. You can examine the size of your residual and stop when it gets small enough, and you below some tolerance. Now, here's a problem though. This is a bad subtraction. Why? Because rk is converting to 0. B is not. B is a fixed vector. A times xk, that's converting to a times x is converting to b. This vector itself is not going to 0. So you're subtracting two vectors that themselves are not small, are not close to 0, but the result is close to 0 as the iteration proceeds. So this is not a good idea. So it's an example of catastrophic cancellation. Two large vectors subtracted give you something small. But we can do something about it. So let's suppose that the difference between two iterates, xk and xk plus 1, is this vector ek. Then here's my residual. So it's b minus a xk plus 1. It's using the definition of residual up here over k plus 1. But then I replace xk plus 1 with this formula, xk plus ek, and I substitute that in here. Then I distribute the a through. So now I have b minus axk, but this is rk. So now what I have is rk plus 1 is equal to rk minus aek. So you might think, oh, we just replaced one subtraction with another. Why should that matter? It matters a great deal. Because rk is converging to 0. E is the error. That's converging to 0 also. So both vectors involved are converging to 0. So now, instead of subtracting two large vectors and getting a small vector, you're subtracting two small vectors and getting another small vector. Cancellation can still be a little bit of a problem, but not nearly the problem that it was using the original definition. So depending on the problem, there are often ways to work around it by treating whatever it is in using a different approach. Sometimes you can rework your formulas, like I did here, to get rid of a problematic subtraction. Well, actually, it happened with one of my PhD students. We found that a formula that in general worked out very well under certain circumstances would have a bad subtraction. E to the x minus 1, where x is small, because you're subtracting two numbers that are 1 or close to 1 and getting something that is close to 0. It turned out we looked at like using a Taylor series and all that, and it didn't help as much as I hoped it would. So we just found a whole other approach. Like we work things at a higher level. But the point is, there was a way to deal with it. Okay. Computers actually use two quadratic formulas. Always been accustomed to, oh, there's the quadratic formula, as in unique. This one right here. Well, no, there are two quadratic formulas. Some students have their minds blown by this. I don't think it's that big a deal, but okay. So, here's an example where something can go wrong. This quadratic equation. So x x squared plus 10,000x plus 1. So the idea here is the coefficient b in your quadratic equation is much larger than a and c. So let's suppose we have 4 digits of precision. Very limited enough. So if I use this quadratic formula with this precision, here are the roots I get. I get a root that's 0, and the other root is minus 10,000. Okay, I have to be careful about this. Okay, I'm going to take a look at which problems I assigned for this homework. So, 3.
You talked briefly about team.
Right. Okay. All right, this is gonna be kind of embarrassing, but I haven't looked at these notes in a while. Now thinking like, oh, okay, these notes are probably present the new second quadratic formula, but no, I do not. It's not here because it's left as an exercise. You all get to do it. Let's see. Wait, did I assign this problem? Number 22. Yes, I did. So yes, sorry, left to reader. But it's from doing things that you know how to do. And I know I have to be extremely, annoyingly coy in the problem statement. Using algebraic manipulation commonly used in expressions involving square roots. And you can get an alternative quadratic formula. Yeah, because, okay, yes. So right here we have, these are the roots I get if I use 4 digits of precision. But if I substitute these roots into the quadratic equation, then this one is terribly wrong because I get to end up with 1 equals 0 if I plug that in. It turns out I have to use at least 8 digits of precision because this is what the root should be. It's a small number. It was just too small for the precision that I had. However, if you rework a quadratic formula, you can get this root accurately without needing that extra precision. Now, what happens is, the reason why we have 2 quadratic formulas is this subtraction, here we have minus b plus or minus the square root. So one of these is going to be a subtraction, because which one depends on whether b is positive or negative. So what will happen is, because one of these could be a subtraction and possibly a difficult subtraction that has cancellation in it, this quadratic formula that you know is safe, if you will, for only one of the roots. Then you rework a quadratic formula, as I was doing in the polar problem, and then that quadratic formula will be safe for the other root. So practical implementations of quadratic equation solvers use both quadratic formulas, one for one root, the other one for the other root. Where instead of having a subtraction, you have an addition, which doesn't incur cancellation. So have fun with that one. Okay, here's another example. 1 minus cosine x when x is very small. Because what happens is, cosine of 0, as you should know, is what? Cosine of 0? 1, yeah. Okay, yeah, so we have cancellation in this case. So, dust off your knowledge of trig identities. So 1 minus cosine x is equivalent to 2 times sine squared of x over 2. So here you avoid that cancellation by running the formula this way. here's another. We have a derivative of sine approximated by a finite difference. So sine of x plus h minus sine x over h. So when h is very small, we have sine x essentially sine x minus sine x. We have cancellation in that case. So you can use this trig identity. Sine A minus sine B is equal to this product of a sine and cosine. Okay. What am I doing here? I was deriving, I think the last time I taught this class, I wanted to derive this fly to make sure I had this right. So, which is good for you all to know how to do this. So, if I write sine A as this, so I'm basically expressing A using this overly complicated expression, and similar for B, then I can use the trig identity for the sine of a sum that gives me this, and then a sine of a difference, which gives me this, and then I subtract these two, and then I get this trig identity. So now I plug this trig identity to my problematic difference quotient. I know I've used the word problematic a lot today. Sorry, not sorry. And they get this expression, which does not have any cancellation-prone subtraction in it. Okay, questions about these examples? The key is to understand why the original expression is not good to use, and how the revised expression no longer has that issue. Oh. Well, this is an example basically the example I did last time. Oh, okay. Similar to it. Oh, how to convert a given number to IEEE double precision. So like here I have a sample X, and I want to get the parts of the floating point number, like the exponent and the mantissa, and in base 2, it's binary. So this formula, taking log to base 2 of the absolute value, and then rounding it down to the next integer, gives me that gives me the exponent of 9. So then, the number is actually stored in IEEE double precision floating point. You take your exponent and you add 1023 to it, and you get 1032. So that's what you're going to store in those 11 bits for the exponent. So if I want to express 1032 in binary, I need to write it as a sum of powers of 2, so like 1024 and 8. And that's 2 to the 10 plus 2 cubed. So this is that number, 1032, in binary. So these 11 digits here are the 11 digits that get stored in the exponent portion. Because if I can represent this number in IEEE double precision, that's 64 bits. 1 bit for the sign. The sign bit is 0 because the number is positive. And then I have my 11 bits for my exponent. So these are the first 12 bits of my internal representation. I still have 52 bits left for the mantissa. Mantissa, I take my number divided by 2 to my exponent. So this is a number I have to represent in binary. But the first digit, the 1, that's to the left of the decimal point, is not stored because generally, floating point numbers are normalized in IEEE, so I don't need to think about that. But what I have to do is keep dividing what's left, or actually multiplying what's left by 2 repeatedly to figure out the rest of the digits. So this process right here, when I showed you something like this last time, is what enables me to get the digits in the binary expansion of this number. And this is what I get at first. Okay, so I carry this out enough to get the next hex digit. So now, if I shift over to MATLAB, and I do format hex, and then I type in this number that I have here, 897.
Starting another diary.
Yes.
Diary.
Yeah, and I'll post this diary in Canvas anyway. So my number is 897.8764. And we'll see what that looks like in hex. Okay, and sure enough, if I flip back to the notes, this is what I had from the signed bit in the exponent, but this is what it is in binary. But if I look at this in chunks of 4 binary digits, 0100 is 4, and this is 0, and then 1000 binary is 8. So 408 are my first 3 hex digits. And then if I'm working out the start of a mantissa, my next hex digit comes from these binary digits 1100, that's equivalent to 12. But 12 in decimal is the same as C in hexadecimal, because in hexadecimal, remember that the numbers 10 through 15 are represented by the letters A, B, C, D, E, F. So 12 is C. And sure enough, the start of my hex representation of this floating point number is 408, and then C for mantissa. And these hex digits correspond to the rest of the mantissa. Okay. Questions about this conversion example? And no, I would never ask you to do this on a test. And there's an example of this in the text also, where it's more detailed. Okay. I have it's from okay. But I want to show you the effects of cancellation. One of the examples I was doing earlier. Okay, so now go back to format long. We'll deal with ordinary numbers from now on. Okay, if I set x equal 1, and if I set h equal to 10 to the minus 5. Now,
You typed 1E.
yeah, this is a shorthand. Okay, so in general, 1e minus p is, where p is a number, is equivalent to 10 raised to the minus p. Now,
To the
so now, if I input this expression, I'll call it expression 1, sine of x plus h minus sine x all over h. So this is something I showed you earlier, that when h is small, that this could be a subtraction that's prone to catastrophic cancellation. So let's see what we get. Okay. Now, I'm going to write a second expression. Remember, I rewrote this formula using sums of product identities. And that expression is 2 over h times sine h over 2 times cosine x plus h over 2. And let's see what that looks like and how it, because these two are supposed to be equivalent. Let's see what actually happens though in floating-point arithmetic. You see that the first several decimal places, they do agree. But the last 4 digits are different. Okay, so the first 11 decimal places of these numbers agree, but the last 4 digits, they don't. Okay. And the fact that h is 10 to the minus 5 plays a role in that, that these numbers are close to each other. So some precision was given away by the subtraction. So I'll make those first 11 digits agree. All right, so that's encouraging. Now let's do this again, but with smaller h. 10 to the minus 10. Okay, if you're following along, you can use your up arrows to bring back this formula for expression 1. Okay.
So we're going back to the expression.
Yes, but now because h is changed, the value is going to be different. And then I do the same with expression 2. Now,
We copy expression 2 and then get a different result.
yeah, and in this case, 1, 2, 3, 4, 5, 6, only the first 6 decimal places agree. Because with h being smaller, this subtraction is even more prone to catastrophic cancellation. We've given away a lot of precision. Now, if you look back to the original expression, did anyone tell me, what is this expression supposed to represent?
Difference question?
What?
Difference question, like the limit?
So what, okay, as h goes to 0, what should this converge to? Derivative. Okay, so, and what should that derivative be in this case? Yeah, cosine. So the exact value is cosine of x. Now, okay. Well, let's take a look. Let's fill in. So exact is cosine of x, which in this case is 1. Okay. Now, let's compare that to the 2 approximations that we have. So, first error will be absolute value of the approximation minus the exact plus over the exact. Okay. And so this is the one that has a catastrophic cancellation. And we see there's some accuracy, it's just not that great. But now if I do the same with the other approximation that does not have cancellation, expression 2, here is much less. So it's just it's not just a matter of the two expressions being different when they're not supposed to be. The one with the catastrophic cancellation is definitely more wrong. That's why it's important to try to eliminate such abstractions from your computations, if you can. Actually, all I have for this diary.
That's the end of the diary.
Yes, actually, it's also made on my notes.
Okay.
So, I guess that means I have time, too much time, for questions on anything, whether it's on the homework or the concept check.
Exploration 1, exploration 2.11.
Okay. 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 All right, so considering being cosine pi over 4, okay, yep. So this is testing your knowledge of data error and computational error. And keep in mind that computational error breaks down into these three subcategories, which point out when reading the quiz, or the concept check quiz. Now, so the first part of the question is about this. If you're trying to compute this, and you're using calculator computer, well, calculator computer can only, so keep in mind that calculators have these limitations. First, you only store limited precision. So here we have an irrational number. And what do we know about irrational numbers? That plays a role in this. Second, computers can only add, subtract, multiply, and divide. Those are its powers. It has no other. They have no other. So, like, if I ask one of you to tell me what is cosine of pi over 6, if you know your trig well enough, you'd be able to give me the exact value. And in this room full of math majors or graduate students, can someone please do that? Cosine of pi over 6. Square root of 3 over 2. All right, very good. Now, a computer's not going to be able to do that. The computer's like, I don't know what cosine is. Write some code for me to do it. That will all involve add, subtract, multiply, and divide, and also like things like comparison. So all of these limitations lead to various types of errors.
Various types of errors.
Whoa, I just made a mistake. Chill out. Various types of errors. Okay. All right. So, and here we have 4 different sources of error described here. So which of these, so the first part of the question is, which of these come into play when trying to compute this, with those
Wait.
limitations?
You mean trying to compute?
Cosine of pi over 4. Yeah,
You mean trying to compute this?
yeah, now, it gives you an answer, but it's not exact. There's, because the exact value is square root of 2 over 2, but, you're not gonna get that exact value from MATLAB. So, so this is where you indicate where is, what kind of, where does data error, computational error come from? Where are we getting, truncation roundup error? And for that, keep in mind, since the computer has no innate ability to evaluate cosine at any angle, how does the computer implement computing cosine? What would be a logical way to do that that takes advantage of what a computer can do as subtract, multiply, and divide? Okay. Now, the other part of the question, which is a more general version of this. I don't know why I put these stupid question marks in here. Like I would never.
So when I solved for cosine pi over 4, it gave me an answer in decimal form.
Yeah, that's all it can do. Okay. Now, so the thing to think about, really for both parts of the question is, there are various types of functions that you've had to deal with across all your math classes. We have polynomials, rational functions, trigonometric functions, exponential, logarithmic, algebraic, and so on. So which of these can be evaluated using only add, subtract, multiply, divide? Okay. All right, without approximating. Okay. Only certain types of functions can be. Which ones? So that's what the last part of the question is about. So if you have a function that does not fall into such a category, what are you going to do? How are you? In that case, you have to approximate the function. How is that done?
So without approximation.
Yeah. So that's what you have to keep in mind for functions in these categories. How can they be evaluated? When I say like algebraic functions, like for instance involving radicals.
Without approximations.
So that's what I'm looking for.
Exponential. What about exponential?
Oh, yeah.
Exponential.
Yep.
Couldn't that be? Couldn't you evaluate that without approximation?
No.
You ask which of these functions can be evaluated using only add, subtract, multiply,
Yeah.
without approximation.
Yeah, because like for instance, take exponential, e to the x can be written as 1 plus x plus 1 half x squared and so forth. The problem is that goes on infinitely. Okay, so which function can be evaluated only add, subtract, multiply, divide using, I want to emphasize this, a finite number of operations. Because if there are functions that can be evaluated using add, subtract, multiply, divide that call for an infinite number of operations, that doesn't count. Because we can't do that. Okay.
How can a function such as cosine be approximated using such a function.
Yeah, so the function cannot be evaluated exactly using abstract multiply and divide. We need some way of approximating it. And what can that be? This is something that actually comes up in, for instance, calculus 3.
Yeah.
It was covered there. Okay. Anyone else have questions, especially on problems in this section?
For problem 9, or exploration 9, I'm just wondering when we are experimentally confirming our forward error estimate.
Yeah.
Are we gonna use Taylor series expansions for the estimator?
Oh,
Those functions? 'Cause there wasn't one given.
you don't need to.
Okay.
Yeah. Yeah, you use evaluate the true functions for that. This problem is not really concerned with any particular approach to approximating these functions. Because if you're using exponential on MATLAB or a calculator, it's going to be approximating anyway.
Now, I do have a question about this one. So, do you want us to provide you with like MATLAB code or write up or text or? It's up to us, like it's just for our own.
Okay, yeah, because the other thing, so what I'm looking for you to submit is, what is the estimate? I would like seeing your work, just so I can assign partial credit. Okay, as far as what's done here. Okay, yeah, if you are going to use MATLAB, a diary would be good, or if you're just going to do this in a calculator and paper, that's fine too, let's scan that. I don't care. Anything more? Cool.
You're not taking too much.
I said we still have too much time left. Well, I guess you wouldn't think it's too much time. Especially
Number 3.
3. Oh, wait, was there a question? Okay. This one right here?
Show that as a relative error and why, and that's why it's hard.
For this, all you have to do is take the definition of relative error that's given here.
It's also right below the question.
Yes, that's me. Yeah, and then rearrange it, and this will come out. So it's just a little algebra at this point. So here, if you say that the relative error, so you set this equal to R, and then rearrange. That's all you have to do.
If that equals R.
Yeah, because it's saying that the relative error and y hat is R.
Assume that equals R.
Yep.
Still done in MATLAB.
No, but this is done on paper. No MATLAB needed for this one. I think there is no MATLAB that's required for this assignment. For certain problems, MATLAB might be helpful if you prefer not to use it, in terms of using MATLAB.
In this case, what if I said Y2?
Y2?
If I substituted that,
Oh, in place of y hat?
yeah.
Yeah, that's fine. As long as I can follow what you're doing. Any other?
So. Or,
4? Okay, so, and here you're just applying the definition of absolute and relative errors, where 3.14, first with 3.14 being y hat, get to absolute relative
three
error.
point four,
3.14,
3.14 becomes y hat.
yeah, that's the approximation. And,
Oh.
and y is pi, the exact value. And then you do that again with y hat equal to 22 over 7.
So y hat is equal to,
First do it with 3.14, and then you repeat the process with y hat being 22 over 7. So
where do we get the regular y from?
that's pi, because these two numbers are both well-known approximations of pi.
So we have to repeat.
Yes.
So. Wait, how do we get 22 over 7 if that's y hat, then?
And pi, and y is also pi. So because both of these numbers approximate pi. Any other?
And that's how we get exploration.
Yes.
What about 5?
Are we doing all of them? So for this one, so this is the second degree Taylor polynomial for cosine of x at the center of 0. So what you do is, first you substitute x from 5 to 4 into here, and that gives you y hat. That's your approximation of the true value y, which is just cosine of pi over 4. And so then you use that to get the forward error. The forward error is y hat minus y. That's the absolute forward error. So using a definition of forward error, so this is the absolute forward error and relative forward error. By this y hat and this y. Then, to get the backward error, keep in mind how, if we look at the definition of backward error, it's x hat minus x. Now, x is given to be pi over 4. To get x hat, you solve this equation for x hat, where y hat is the approximation you computed earlier, and f is cosine in this problem. And once you have, so you solve this equation to get x hat, and then you plug that in here to get the backward error, the relative backward error. So then once you have your forward and relative backward errors, okay, yeah, okay, that's, and then you do the same thing for the fourth degree Taylor polynomial, which has an additional.
You ask where the forward and backward errors of this approximation,
Yeah.
what are the relative forward and relative backward errors?
Yeah, so there's 4 errors in total, but you get them using this definition for forward error and this definition for backward error.
And then the relative backward error is that?
Yes. Yes, so these 4 formulas for your forward error, relative forward error, and then your backward error and relative backward error. So you do that for,
Delta. The one for delta y is the forward error.
yes. So you do that for this second degree Taylor polynomial for cosine, and then you do it again for the fourth degree Taylor polynomial, which is this plus an additional term. It's like 1 minus x squared over 2 plus x to the 4th over 24. And what you should find is for a fourth degree Taylor polynomial, the error should be smaller because that's a better approximation. Take a look at the list of problems.
Repeat this for the fourth degree.
So this is the second degree. Fourth degree is 1 minus x squared over 2 plus x to the 4th over 24.
X to the 4th over.
24.
So for exploration. X to the 4th plus.
Plus 1 minus x squared over 2 plus x to the 4th over 24.
Plus 1 minus x squared over 2 plus
x to the 4th over 24.
that.
Yes. Okay. Are there any other more questions? Or questions about something else, like a concept checked or whatever you got? I'm not going to obligate anyone to stay. I probably should have said that 5 minutes ago, at least. Okay. But or you can stay, at least answers to any questions might be helpful to you. So it's up to you. I will stop the recording.